Hello, welcome to this third part. Right, this is the two-level system. I divided in 3 lectures so I could explain well to you what's going on when the atom, when the matter considered as a two-level is interacting with the oscillatory electromagnetic field. Last lecture, we ended the lecture in a very nice situation where we could identify, A2. Remember, we have a two-level system. 1, 2. A2 square represents the probability to be here. A1 square represents the probability to be here. And this is everything that can happen. And then we have electromagnetic radiation coming here with frequency omega. And we observe that the probability to start with the system here. We start with the system here. And we end here. Varies in time. And this is the plot of this. The probability to be here, starting here, grows with time if delta equals to 0, reaches 1, comes back, oscillates. If the delta, which is the detuning, which is the difference between the frequency of light and the energy of between the two levels expressed in frequency, is bigger, either positive or negative, this oscillates with smaller amplitude and faster, and this we call a coherent superposition of those two states caused by the radiation. Well, we made many observations, and I explained to you that what's happened is the radiation interacts with the system, transform that cloud, the probability of being in another state, and I use as an illustration the S and P state of an atom, because that's clear that the oscillatory part of the electromagnetic field will deform this to be like this, and then will compress this to be like that, and this keeping oscillating with a typical frequency that is called Rabi frequency, and when you have a detuning is the modified Rabi frequency. And then I made an analogy that this is like a two-coupled pendulum. One with some characteristic frequency, the other with another characteristic frequency, coupled by a spring, and I put one to oscillating, holding the first. And these migrate the energy. So this is like having the atomic system as one oscillation, one oscillatory system, and the light as the other oscillatory system. So this is like energy being transferred to the energy being transferred from one oscillator, which is the electromagnetic field, to the other oscillator, which is the two-level system. Very interesting analogy. And we, of course, has to tell you a few more interesting situations here. We did an example that we start the situation with we turn on the field where the system was in level 1, the lower level in energy. But we could start with the atom in level 2, or the matter in the higher energy. Right? Okay, that's the two situations we can deal with. Now, interesting is that we turn on the field. The system is in level 1, so in t equal to 0, we can say that A1 is equal to 1. And then we wait time enough for A2 goes to 1. And then we stop. If we stop, the system remains in level 2. We made what we call a transference from level 1 to level 2. Let's imagine that we turn on the electromagnetic field. We transfer the probability for the system to be in level 2. Means the system will be in level 2 now. If you do a measurement, it's 1 probability to be in level 2. And then later on, we come later, and we turn on again the field. We turn off the field, the system stays there. in level 2. Later, we shine the field again. We turn on the field again. If we do that, if we turn on the field again, what's going to happen is you start in level 2, now the system comes down and increases the energy of the field. I explained to you. But what I did not explain to you is that the way the system is, it remains whatever you put. So if you transfer the system to level 2, and if there are many molecules or many atoms, and you did that in the right time, you illuminate time enough for the system to start here, grow up, and stays in here. Then I cut it. So practically speaking, all the population is in level 2. If you're not taking the population from this level, it stays there. When I shine again, the things continues from that. If my field is in phase with this oscillation, if it is like I continue there with my, but I turn off. But I keep oscillation, but without shining. If the system comes back, starts from the point that left and bring the atoms down. When it brings the atoms down, increase the energy of the field. So I can remove, I have a whole population there. I take that energy, put back in the field. That's possible. Of course it is. But I want to show you this picture in terms of photons, even though we made a semi-classical approximation. But I can do with photons, because that's the laser principle. How a laser works. Laser works the following way. I have a two-level system, let's say. I start in here, and I shine some photons. I transfer the population to here. Now my system is here. And I wait. A little late, the system is there. If nothing is taking the system from there, it's still there. I put some more light. I put another photon. This other photon cannot be absorbed because there is nothing that will take this energy. The only thing that can happen is this photon provoke the system now that's originally here to come down. And what's going to do now? He's going to add to the field. The field originally had one photon, but now this field stimulated this guy down. So it's like the system starts with probability to be in level 2, 1 probability. It is here. The only thing this photon can do is remove the thing here, add the energy to the field, and make this field growing together. And it's add the energy on the oscillatory part of the field with the same frequency there was before. So we use it to say that's like adding to the same mode of the electromagnetic field more energy. And this is the principle of the laser. This is what we call the pump part of the laser. We pump energy to the system, and that's the emission part of the laser. First I give energy to the matter. The matter accumulates in some excited state. And then the photon comes, brings down in the stimulated process, and add a twin brother for the photon. It adds in the same mode of the radiation the energy. Doesn't go to other place. Goes exactly to the... So if I measure the electromagnetic radiation later here, it is like the amplitude increases a little bit. The intensity increases a little bit. Right? And this is the principle of the laser. What the laser is I pump energy to a system, and the light brings the system down, adding energy to the electromagnetic field that comes in the same direction of this one. So I amplify the intensity of a field going in one direction that was the one that stimulated the process to come down, because that's the mode that has to receive the energy of the electromagnetic field. That's a very important application of all this. Now, there is one thing I have to tell you here that I did not tell you. Up to now, our system has always been stable. Level 1, level 2, doesn't matter. If I put there, nobody could take out. This is not true. You know, we always put a situation that is, in reality, is a little more complicated. When I have a system that's not in the ground state, it may decay spontaneously. And this is the process that we call spontaneous emission. So spontaneous emission is present. I put the system in a level, and the level may come down. So it's not like the way I said to you, but there are something else involved. What causes the system to come down? Well, that's a very interesting question. And that was solved by many scientists like Schwinger, Feynman. They formulate what they call the electroquantum dynamics. Because when you produce an atom, it is in excited state. I just showed to you that light will provoke the atom to come down. But you believe that when I have an atom in the vacuum, there is nothing around. But what those guys prove is that there are some oscillations, fluctuations in the vacuum. And that sometimes photons appear and disappear. And during these fluctuations, they may interact with the atom. And when they interact, they may cause the atom to come down. That's a proof that the nothing is not really nothing. The vacuum is not really nothing. There are fluctuations in field there. And this causes what we call the spontaneous emission. To really calculate the spontaneous emission, you have to take those things in account. You have to quantize the space, and you have to put the atom in the context of the vacuum with fluctuations. And that causes, you can imagine, those photons pumping, you know, like coming, interacting with the atom that's excited and eventually brings down. And this spontaneous emission is a loss in the system because it due to the fluctuations of the vacuum, or you know, things like this. And the photon can go everywhere, not exactly adding energy to the field, but putting energy to the universe, to the vacuum. It's not putting energy back to the field, the original field. It's putting energy everywhere. That's why spontaneous emission puts light everywhere. Right? Okay, but that changed a little bit the context that we create. Because we put, oh, and by the way, depending on the system, we may have a different lifetime for this to happen and everything. So this is very characteristic of the physical system, and we use this. We use this loss of energy of the excited system as sometimes a fingerprint for the system itself. But what I explained to you must be little modified. We have to change the equations because now we have a loss. That is a loss mechanism, taking energy from that system, putting somewhere else. The system will not oscillate very nicely, preserving energy between the field and the atomic system in a coherent way, as we said. That will be destroyed because I excite my system, and then eventually the system will put the energy out of this, put energy to the vacuum everywhere in the world. And I want to put that in my equations, this loss channel that the spontaneous emission represents. Because it's taking population of the level 2. Of course, where is the system going when the system emits light everywhere? Comes back to 1. So the atoms still are either 1 or 2, but the light is going some other place. And this breaks down that nicely coherent oscillation of the electromagnetic field together with the atom, oscillating in time by the Rabi frequency and everything. That breaks that down. Okay. Well, we're going to change a little bit the system now. This is the excited state in pink. This is the ground state in blue. The electromagnetic field comes, and I am adding a rate of spontaneous emission. So that is a rate. That is a number of spontaneous emission per unit of time that can happen. So we're going to add this rate of spontaneous emission, right? So add gamma, capital gamma, is the rate of spontaneous emission that must decrease the population of level 2 and increase the population of level 1. So here I show to you that the spontaneous emission brings energy out of the system, but not population. The population will come down and will come to level 1. So then you can see that what's happened before putting the equations. The spontaneous emission decreases with the time in the population of level 2 because takes energy out and increase the population of level 1. Remember those equations we had? I have to get back for you. We build up those equations. You know, that's the variation of the coefficient level 1 and level 2, remember? We had those equations, right? And we're going to consider delta equal to 0 now, just for clarification. But we can consider any delta you want. That's no big deal of that. The time variation of the 1 and 2 coefficient, I don't think it's this transparency. Let me get it. You know, I had the equation before. Here it is. This is the equation we had. Sorry to tell you that. Remember, this is the Rabi frequency. A1 dot, which is the time variation of the probability of the coefficient that will determine the probability to be in level 1, is the I Rabi frequency divided by 2A2 times this time oscillatory term. And this is delta. Remember, we call omega minus omega 1, 2 of delta, the detuning, and A2 the same, but then there is this plus here. That's a term that normally we're going to throw away. Okay, so that's the equation I'm going to recover from lectures before. In a previous lecture we had. And now I'm going to add the spontaneous emission. We know the spontaneous emission, so that's the part we had, remember, up to here. Now I'm going to add this. Why this is positive? Because, first of all, for the spontaneous emission to increase the time variation of the population, it is a positive term. But I must have population in the level 2. So it must be proportional to 2 for that to take place. If A2 is 0, there is no way of spontaneous emission. So it must be proportional to terms 2, and it must be positive, and it is gamma, the rate divided by 2, because in average I'm going to go from here to here and from there to here, right? So the 2 here, it's a very significant, because we are dividing the probability. You know, this is gamma over 2 because we are taking population from here and putting population from here in average. So the A1 add this term because the gamma represents the rate of spontaneous emission. It's increasing the population of level 1, so it's positive. But it's negative for the population of level 2 because the spontaneous emission is decreasing this. So must add, it's negative because it's decreasing, and still must be proportional because will not take place if there is no population on the level 2. So we add the 2 extra terms on this. We add the 2 extra terms. That makes things a little more complicated. Because now we're going to have to do again, take the this is the coupled differential equation system now in the presence of spontaneous emission. And we have to solve again. We're going to have to take the time derivative of one of them. I'm going to take of the second one. And in the place of A1 dot, I'm going to put this guy here, which depends on A2. right? And then I can come with the equation on A2 itself, and I can do the solution. This is not a very hard solution to do. You can do yourself, the time derivative and putting together the terms and everything. Still we have A1 square plus A2 square equal to 1. We still have that. That's the conservation of probability. And you come with the solution. It is a long expression, and I'm going to express that in the graph, in the plot. Well, always you have something taking energy, you have dumping. You have to kill the oscillations. This is traditional in any physical system. And here, this real term in here, that's what means, if this was complex, means oscillatory again, like this. But because this is real, that introduces dissipation, that will introduce decay of the oscillations. We know that when we study mechanics, when we study quantum mechanics, always we have a term killing the oscillations when we have terms like this. Spontaneous, that's why we say that spontaneous emission represents a dissipation in the system. Spontaneous emission is like a dissipation. The system is dissipating energy, putting energy in other things besides the atom and the electromagnetic field that's causing the excitation. So what's happening with the probability? We start, let's do the same thing. We start with the population. A1 in t equals to 0 is 1. Means that we start with the population, we have the two levels. In t equals to 0, we start the population in level 1. And what the electromagnetic field is going to do between level 1 and 2 is promote transition. Of course there is oscillation, but we have that dissipation taking energy out in a rate gamma, which is the spontaneous emission. What the solution showed to us, and you are welcome to do it, is that A2 square, which is the probability to have in the system, in the upper level now, starting in the first level, it grows. We can prove that this grows square with time, and there is an oscillation. Do not reach 1, because there are dissipation going on now. It's taking energy of the system, oscillates with the Rabi frequency modifier and dies out the oscillation and reach a level, which is the final value of, I turn on the field now, the system goes and take it to a stationary state for a final value of A2, which is square, is the final transition probability for the system now. And this has a wonderful form. The probability of promoting the system to level 2, which is the limit of A2 squared as the time grows, is a wonderful Lorentzian type. That's an important relation to know. The probability of a transition when spontaneous emission is present. So the system oscillates as before, but then the dissipation introduced by the spontaneous emission makes the oscillation dies out, and the system reach a final probability to be in state 2, of course, and state 1. This is the probability to be in state 2. 1 minus this quantity is the probability to be in state 1. You can calculate. Now, imagine I put a large intensity. Remember, omega Rabi square is proportional to the field square, to the amplitude of the electromagnetic field square, which is proportional to the intensity of light. So the Rabi frequency square is proportional to the intensity of light. So when the Rabi frequency square is much bigger than these other terms that appear in the denominator, so it's like this is the dominant effect, and this comes to 1, and the probability is half. That's the famous statement that when I saturate the transition, put a lot of energy through the intensity of light, the probability to have the system there, the best we can do is half. The best we can do is having half of the system in an excited state, half of the system in the ground state. To be able to really transfer, I have to work in finite time, where I transfer population bigger than that. If I go to saturation, put a lot of light, thinking that I'm promoting everybody up, I'm also promoting everybody down. And the compensation of all those effects takes to the saturation phenomenon. And gamma here is a very important aspect of this. And in a normal situation, the gamma here is somehow giving to you a term in the denominator, which will give also a line width. Remember, delta, right? Delta is the detuning, which is the frequency of light minus the frequency of your system. If I make a plot of the probability of transition as a function of delta, you know, I'm going to find, let's say that delta equals to 0 is here. I'm going to find a delta where the probability is maximum and then decays. This is a line width. And this line width depends on the existence of the dissipation. If the system, if this is 0, this collapses. This will depend on gamma. This will be strongly dependent on gamma. And of course on the intensity, because there is what we call a power broadening of the lines. So this, if I put more and more power, this resonance curve will broaden up a little more and more. And everything is in this curve. This is a saturation, the way it's preserved, is a full quantum effect. This doesn't happen in the classical oscillator. If this was a classical oscillator, probably putting more energy, I'm going to blow up things. I will never really saturate. So the presence of the dissipation by the spontaneous emission stop the oscillation and produce a loss of coherence. The system do not oscillate anymore in a coherent way between being in the excited state and the ground state. Okay, so with this extra part, I concluded what I want to tell you about the two-level system. The two-level system is a very important approach for us to deal with interaction of radiation with everything, including many, many spectroscopic techniques and everything. So I hope you appreciate the explanation. So we went through the fundamentals of it, and we could understand a little more those effects. This lecture is considered as a supplement, as an extension of the previous lecture on the two-level system. Okay, now in the next lecture we're going to apply this for real applications that we have in the domain of light interaction with the system, in the biomedical applications, and many other applications in engineering in general. Bye-bye, see you then.